Chapter 18 is about solubility and making up solutions. We've done some of this previously, but now we're going to learn how to make up precise solutions with a precise concentration by looking at the molarity. Okay? Let's review a little bit about solubility though before we start looking at molarity. Solubility is the amount of substance that dissolves in a given quantity of a solvent at a given temperature. Okay, so for example, if I want to make up a salt solution, I can take some tap water and I can take a beaker and I can add some salt to the beaker, and the sodium chloride solid would dissolve in the solution and I would get a saltwater solution. Okay? If I just kept adding salt and adding salt and adding salt, eventually it would get saturated. And that's what a saturated solution is. It won't hold any more of the solid. Okay? Let me show you what I mean. So if I add some tap water to this, and I add some salt water to it, okay, it'll start to get cloudy. Now I'll stir that. And you see it get cloudy as the sodium chloride is dissolving in the water. The sodium ions and chlorine ions are being pulled apart, and it will get cloudier and cloudier. As I keep adding salt, eventually it's going to get to the point where it's saturated with salt, and it will settle out on the bottom. It won't hold any more. Okay. Another way to illustrate that, I've got a test tube here, and it's got sodium sulfate decahydrate dissolved in it. Okay, and it's saturated with it. And I've cooled it down. I'm going to add a seed crystal to it, and this is a good illustration of a saturated solution because if it works, when I add this seed crystal to it, the whole thing will crystallize. So it's just ready to crystallize now. It's totally super saturated, we call it. Let's see if we can get it to work here. So I'm adding some crystals to it. I'll hold it up close to the camera here. Those seed crystals just act as a site for the rest of the sodium sulfate in the solution to attach to, and eventually, because it's super saturated, the whole thing will crystallize. See the crystals forming? So that's a super saturated solution. It won't hold any more of the sodium sulfate decahydrate. It's completely saturated. Okay, and it crystallizes. So that's a good illustration of a supersaturated solution. Alright, so a saturated solution is completely full of solute. The solvent won't hold any more. An unsaturated solution will hold some more. Okay? Somewhere in between there is what we're usually striving for when we're making up solutions. We want it at a certain saturation level, and that's when molarity comes in. Molarity is a measure of how many moles of solute are dissolved in a liter of solvent. Okay? And we'll show you those calculations in just a minute. Before we do that, let's talk about miscible and immiscible. If I put two liquids together and they are miscible in each other, they will dissolve in each other. So for example, if I take some water, okay, this is just water, and I add alcohol to it. Water and alcohol are miscible because part of the alcohol, the structure of it, is the hydroxyl group OH, which is polar, and water is polar. So if I mix water and alcohol, I just get one layer because they are miscible in each other. It may take it a minute to reach equilibrium and spread throughout all of the water, but eventually it will be completely dissolved in that water. Okay? But if I take mineral oil, and remember oils are non-polar. Water is a very polar molecule. Oils are very non-polar. So if I take water and I add mineral oil, I get two layers because oil and water don't mix. Oil is very non-polar, water is very polar. So I'll get two layers forming, the mineral oil on top, the water on the bottom, because they're immiscible in each other. Okay, water and oil don't mix. Okay, so factors affecting the solubility. Now, if I warm a solution up, it will hold more salt water. Okay, I can get more to dissolve in it if I warm it up. And this table illustrates that. In the liquid phase, as the temperature goes up, the solubility goes up. Okay? As the pressure goes up, it really has no effect on the liquid dissolving, the solid dissolving into a liquid solvent. But gas is a little different. As the temperature goes up, the solubility of the gas in that liquid goes down. Okay, because the gas molecules want to leave the liquid and evaporate out into the atmosphere. And if I warm it up, they'll do that more quickly. Okay, so as temperature goes up, solubility of gas goes down. And as pressure goes up, solubility of gas goes up. So if I've got a gas in here and I put it under pressure, I can get more of the gas to go down into the solution. That's what carbonation is about in your soda. When you open the cap on your soda pop and you hear the gas escape, that's carbon dioxide gas escaping out. It was in the soda, dissolved down in the soda because of the pressure. But when you release that pressure, then you can hear the gas escaping. Okay, I've got another way to illustrate that. This is going to show you, I'm going to breathe out carbon dioxide gas into this solution that's got a pH indicator in it. And what a pH indicator is, it's a dye that changes colors as the pH changes. So this particular indicator is blue in a basic solution. And remember, a basic solution has a pH of above 7 up to 14. The closer you get to 14, the more basic it is. Okay? An acidic solution, below 7 down to 0. Like stomach acid is a pH of like 2. It's very acidic. With water being neutral in the middle, it's 7. Okay? So this is in a basic solution, and this particular dye is purple when it's in a basic solution, green when it's neutral, and yellow when it becomes acidic. So I'm going to saturate this with a gas by just bubbling into it. Okay? I'm just going to breathe into the straw and bubble carbon dioxide into this pH indicator. Okay, you can see it's gone from basic, which was purple, the indicator is purple in a basic solution. As I breathe carbon dioxide into the solution, it turns into carbonic acid. CO2 in water makes an acid, carbonic acid. So I've lowered the pH. It was above 7. Now it's green, which is right around 7. The pH is 7. If I continue to breathe carbon dioxide into it and continue to saturate this solution with a gas, it'll hold only so much carbon dioxide, but it will change the pH to acidic and turn yellow. Okay, so now it's acidic. There's quite a bit of carbon dioxide in there. If I put it under pressure and continued to blow, if I could do that, I could get more carbon dioxide to dissolve in the solution and get it even more acidic. But what I'm going to do is I've got a hot water bath going here. This is just tap water that's being warmed up. I'm going to put this down in this tap water. And I'm going to leave it in there. And hopefully it's going to illustrate how if I increase the temperature, I decrease the solubility of the gas. So we'll check this in just a few minutes. But if it works the way I think it will, carbon dioxide is going to leave out the end of this tube. The carbon dioxide that I saturated this solution with, that I breathed into it, is going to evaporate out because as this hot water bath heats up that solution with the pH indicator in it, the molecules will start vibrating more quickly and the gas will escape faster. So we'll set this aside and see if it will just slowly turn back green again as carbon dioxide evaporates out of it because of the lowered solubility as the temperature goes up. The pH should go from acidic to more neutral or basic. So we'll check that in just a few minutes. Okay? All right, let's talk about molarity. Now, the definition of molarity, let me grab my marker. Is moles per liter. Okay, molarity equals moles of solute and remember solute is what's being dissolved in the liquid per liter of solution or solvent, I should say. So it's a measure of concentration, okay, how concentrated the solution is. The higher the molarity, the more concentrated it is, or in other words, the more solute there is per liter of solvent. The lower the molarity, the more dilute the solution is. Dilute means it doesn't have very much solvent in it. Concentrated means it has a lot of solvent in it. So when we're doing chemical reactions, we want to know exactly what molarity of a solution that we're making up. This one says 4 molar NaCl. It's going to have a lot more salt in it than if I make up a solution of 0.5 molar NaCl. So this one would be dilute, or more dilute, than this one, which would be more concentrated because it would have more salt dissolved in the same amount of liquid. Both would have 1 liter, okay, but one would have more salt in it than the other. Let me show you what I'm talking about. So the first problem we're going to solve is find the molarity if you have 0.5 moles of sodium chloride dissolved in 0.05 liters of solution. Okay, so they're telling us we've got 0.5 moles of sodium chloride in 0.05 liters of water. Okay? So to find molarity, just simple math. Divide 0.5 by 0.05 and you get a molarity of 10. Okay, so if I solve this, I would have a 10 molar solution of NaCl. Okay, pretty straightforward. Let's try another one. Okay, it says if I had 0.5 grams of sodium chloride and I dissolve it in 0.05 liters. So now I've got 0.5 grams of NaCl in 0.05 liters of water. Now I got a problem because molarity is moles of solute in liters of solvent, and they're giving me the sodium chloride in grams. Okay, so I've got to convert grams to moles. Well, that's easily done. You just need the periodic table and maybe a calculator. First thing I got to do is figure out how much does 1 mole of sodium chloride weigh. Well, that's what the periodic table tells us. Okay, as you find elements on here and you look at the atomic mass, that's the number, usually the bigger number. It usually gives you the atomic number for each element and the atomic mass. Most periodic tables do. The atomic number, remember, is the number of protons in the nucleus. The atomic mass is the number of protons and neutrons in the nucleus. So it's actually the weight of the nucleus, and that's what we need to know. So if I look on sodium here, it says, it's in column number 1, element number 11, 22.99 is the atomic mass. Okay, so I'm going to round that up to 23. So as I figure out the weight of sodium chloride, I've got 23 grams for sodium. And then I look at chlorine. Chlorine is in column 7. Right here, it's element number 17. I look at its atomic mass. Remember, that's the bigger number of the two. If it has the atomic number, which is 17,